Picture waking up, padding across the floor, and realizing that beneath the quiet familiarity of your home lies a geologic engine powerful enough to redraw coastlines and dim the sun. That scenario isn't a thriller premise, but the sober truth behind Earth's supervolcanoes, immense systems scattered across the planet that slumber for ages, then occasionally erupt with a force that bends climate, devastates ecosystems, and imprints a scar in the rock record that endures for hundreds of thousands of years. While you're reading this, roughly 20 such giants bide their time. Ordinary volcanoes already command respect. Supervolcanoes operate on a scale that defies intuition, capable of triggering volcanic winters that outlast a human lifetime, and of turning a globalized civilization into a fragile network struggling under ash-choked skies and failed harvests. Comparing a typical eruption to a supervolcanic outburst is like setting a sparkler beside a city-leveling detonation. The difference isn't just size, it's consequence. A recent reminder arrived from the South Pacific. In January 2022, the submarine volcano Hunga Tonga Hunga Ha'apai ruptured with astonishing violence. The blast's acoustic shock circled the globe and was audible as far away as Alaska, over 6,000 miles, 10,000 kilometers from the source. That single eruption hurled tsunamis across the Pacific Basin, pushing 2-meter crests onto shores that had never heard of Tonga the day before. The island chain sits some 1,243 miles, about 2,000 kilometers, northeast of New Zealand, along the restless rim we call the Pacific Ring of Fire, where descending oceanic plates fuel a majority of the world's volcanic activity. Eruptions are part of Tonga's geological biography, but this one shattered expectations. It lofted a column of ash to roughly 36 miles, 58 kilometers, punching through the troposphere and into the stratosphere, and it expelled on the order of half a cubic mile of material, near 1.9 cubic kilometers. Imagine filling a vast open-pit excavation. Think of the famous Mere Diamond Mine, with ash and pumice, until the horizon is rimmed with gray walls. Even then, you only begin to visualize the mass involved. And still, on the Volcanic Explosivity Index, the VEI, that cataclysm rated around a 5 or 6. The scale runs to 8. In other words, the geologic archives preserve eruptions hundreds of times larger, events that could reframe human history in the span of a few bad harvests. The VEI functions like a ruler for eruption magnitude. It doesn't just tally volume, it also weighs how high the plume rises and other traits that hint at regional and global reach. At the quiet end are VEI zero effusions, the gentle glowing rivers of basaltic lava familiar from Hawaiian fields. Climb the ladder in the hazards compound. VEI 2 covers frequent Strombolian fireworks. Mount Etna's persistent activity is spectacular, yet comparatively modest. VEI-3 takes us to episodes like the 1990s Soufriere Hills crisis on Montserrat, when ash and pyroclastic flows transformed a Caribbean island and drove long-term evacuations. At VEI-4, the 2010 Eyjafjallajökull eruption in Iceland grounded planes across Europe, illustrating how microscopic ash glass can erode turbine blades and render a modern air network useless almost overnight. The disruption wasn't local. It cascaded through supply chains and family plans, a reminder that our webbed world is exquisitely sensitive to small particles lofted high. Now move into the truly consequential tiers. VEI-6 eruptions don't just devastate their backyards, they tug on the global thermostat. In 1991, Mount Pinatubo in the Philippines injected a veil of sulfur-rich aerosols into the stratosphere, scattering sunlight and modestly cooling the planet for a stretch. Step back to 1883 and Krakatoa's eruption in Indonesia, a detonation so fierce that twilight skies were reported as strange and blood-red for months, the kind of atmospheric palette that may have inspired the haunted tones of Edvard Munch's The Scream. Even these notorious events are outclassed by VEI-7. In 1815, Tambora erupted with a ferocity that pushed 1816 into legend as the year without a summer. temperatures dipped by about half a degree Celsius on average, just shy of a degree Fahrenheit. Yet that small numerical change translated to crop failures, cold rains, and social stress from Europe to North America. A fraction of a degree, multiplied by an entire growing season, can turn abundance into scarcity. VI8 sits beyond living memory. This is the supervolcano tier, where ejected volumes exceed 240 cubic miles, about 1,000 cubic kilometers. Tambora's output is dwarfed by a factor of 20. Tonga's is belittled by a factor of hundreds. Picture a block of rock and ash the height of Everest, and still you won't quite capture the bulk. Because these giants rupture so rarely, no scientist has witnessed one firsthand. We reverse engineer their savagery from the evidence they left. Ash blankets that stretch across continents, layers in ocean cores that tell of months of dimmed sunlight, immense basins where the ground collapsed after the magma chamber emptied, leaving a caldera so broad it reads as a lake from space. The absence of direct observation creates a knowledge gap. We understand some precursors: earthquake swarms, ground inflation, shifts in gas chemistry, but we do not yet possess a crystal-clear profile of the signals that would mark the countdown to a VEI8 event. Nature doesn't issue schedules, it etches hints. One of the latest super-eruptions in Earth's story unfolded roughly 26,000 years ago in New Zealand. The eruption excavated what is now the Taupo caldera, an amphitheater of subsidence that holds a deep blue lake reaching about 610 feet, or 186 meters, and spanning nearly 46 kilometers at its widest. The violence required to drop a landscape of that size is difficult to imagine. Travel farther back, some 74 millennia, to Sumatra's Toba eruption, among the fiercest blasts our species has survived. Toba expelled at least double Taupo's volume, likely much more, and left behind a caldera now filled by a sprawling lake, encircled by uplifted, scarred terrain. The climate perturbations associated with Toba remain debated, but the scale of sulfur and ash implies years of dimmer daylight, altered rainfall, and ecological stress that would have tested any population without modern buffers. The physics behind climate-scale impact comes from chemistry locked inside rising magma. Deep underground, molten rock holds gases under pressure: water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide. As magma ascends and confining pressure drops, those dissolved gases attempt to break free, like fizz racing out of a shaken bottle. In sticky, silica-rich magmas, the kind often feeding supervolcanic systems, bubbles can't escape easily. Pressure builds, the system fractures, explosive fragmentation hurls ash skyward. Among the emitted compounds, sulfur dioxide is a climate lever. Lofted into the stratosphere, it oxidizes and condenses into a veil of fine aerosols, sulfuric acid droplets, and related particles that reflect a portion of incoming sunlight back to space. That mirror dims the surface, cooling the lower atmosphere and, over months to years, reshaping wind patterns and rainfall belts. Pinatubo offered a modest modern demonstration. Super eruptions write the message in all caps, potentially sustaining a volcanic winter long enough to starve forests, stall monsoons, and exhaust granaries. All of this sounds apocalyptic, but it is, above all, a lesson in timescales and preparedness. Super eruptions are vanishingly rare on human calendars. The odds of one in any given decade are small. Yet geologic time is patient. Given enough centuries and millennia, recurrence is not just possible but inevitable. That tension, low annual probability paired with extreme consequences, poses a unique challenge. It's easy to ignore until it isn't. Practical resilience begins with measurement and humility. Satellites track ash and sulfur. GPS networks watch the ground breathe, rising millimeters to centimeters as magma intrudes, sinking as systems relax. Seismic arrays map the brittle crust, cracking and creaking under new stress. Gas monitors sniff for changes in carbon dioxide and sulfur that hint at fresh magma. No single metric tells the whole story. A mosaic of signals does, and even then, the picture can blur with false alarms and ambiguous data. The path forward isn't prediction with absolute precision. It's better surveillance, better models, clearer communication, and plans that scale from local evacuations to international food reserves when the sky grows hazy. Zoom back to the human frame. In a connected world, a supervolcanic veil wouldn't respect borders. Jet routes would reconfigure or halt. Solar power yields would dip beneath ash-dimmed skies. Harvests at higher latitudes might fail in a string of cold summers. Tropical rainfall bands could shift, punishing one region with drought while drowning another. Supply chains, already sensitive to comparatively mundane disruptions, would strain as staple crops faltered and shipping corridors adjusted. None of this is a reason for paralysis. It's a case for viewing deep-time hazards the way we view insurance. Unlikely this year, costly to ignore over the long run. Investments in diversified agriculture, resilient energy systems, and strong scientific institutions are not abstract virtues. They are the kind of quiet scaffolding that holds when the rare, brutal chapters of Earth's cycle turn their page. All the while, the planet keeps writing and rewriting its own story in basalt and ash. Supervolcanoes are not villains so much as reminders. Our species occupies a world where continents drift, ice sheets breathe, seas rise and fall, and every so often, a buried cauldron exhales, with enough force to reset the stage. The prudent response is neither fear nor denial, but a steady attention to the clues, a willingness to learn from the last time Earth spoke this loudly, and a commitment to keep people safe when it speaks again. Somewhere, far below a placid lake or a grassy plain, a chamber is cooling, another is warming, and pressure is moving through fractures we cannot see. Whether the next century passes with quiet steam or a sky-filling cloud, the work is the same. Understand the machinery, build buffers against the worst case, and stay curious about a planet whose power dwarfs our own, even as it sustains us. Sicily's towering fire mountain looms over the island's east like a restless cathedral. Mount Etna, in southern Italy, is not only large by European standards, it is the continent's most energetic volcano, a place where the crust moves and sometimes roars. Its summit stands near 10,825 feet, about 3,300 meters, though the exact number shifts with each outburst as craters build and collapse. For centuries, Etna has cycled through eruptions and pauses, becoming both a research site and a major attraction. That appeal comes with a sober reality. Beauty and danger share the same slope. Etna's behavior does not follow one simple script. It moves along a spectrum, from modest Strombolian pops and ash puffs to short, intense episodes that fling columns of molten rock skyward. In the latest chapter, fresh lava has again threaded down the flanks, cutting glowing rivers through black scoria, while orange fountains light the night. Authorities tightened access, keeping people below roughly 8,200 feet, about 2,500 meters, while instruments flagged elevated shaking. The goal is straightforward: admire the show, but keep distance while the mountain's pulse is high. A new feature has become the focal point of concern, a visible fissure on the upper slope. Drone surveys and handheld footage make the crack unmistakable. This is not a surface blemish. Fractures like this reflect underground stress as pressurized magma pries rock apart. Such openings can precede larger events, lateral eruptions lower on the cone, or, in more severe cases, structural slumps that peel away portions of the flank. Scientists have long measured a slow, persistent slide of parts of Etna seaward, a creep that usually proceeds at a walking pace each year, but hints at the forces at work inside the edifice. In rare cases elsewhere, sudden volcanic slope failures have even kicked up waves. That is not a forecast for Sicily, but it explains why a new crack instantly raises the stakes for monitoring. Even as lava fountains and glowing streams seize the eye, the volcano's internal heartbeat, the tremor signal, continues. It strengthens and dips, but together with surface deformation, it points to a system under pressure. Volcanologists are asking a simple question with complicated implications. Is this a familiar pulse in Etna's rhythm, or the start of a deeper reshaping of the mountain's plumbing and flanks? The fracture sits just below the summit crater complex in what specialists call a subterminal zone near the 3,000-meter contour. That belt is notorious among Etna watchers because stress can accumulate there until the volcano chooses a side vent instead of the summit. Flank eruptions are disruptive. They can open abruptly, cross trails and roads, and send lava toward valleys long unused to flows. Their unpredictability raises risk for hikers, workers, and nearby communities alike. Ground sensors show deformation consistent with magma intrusion, hot material wedging into cracks and lifting the surface. Bi-amount satellites detect even when people notice nothing. The new fissure is likely the surface expression of that push. If intrusion continues, modest activity can escalate into stronger paroxysms, or if rock fails, into local collapses. Recent aerial passes mapped several small vents feeding multiple lava tongues. As they descended, the flows split and rejoined like braids in a river. The farthest fronts reached about 7,546 feet, around 2,300 meters. Higher up, the summit vents above, roughly 9,843 feet, near 3,000 meters, continued to supply fresh magma, turning the upper slopes into a moving assembly line of incandescent rock. In parallel, Italian civil protection raised the alert posture. An F1 advisory signals heightened caution and keeps the summit effectively off limits. Should conditions escalate to an F2 stance, as happened earlier this season, authorities would warn about fast-moving hot clouds and sudden hazards. A recent dip in seismic chatter may look like relief, but lulls on Etna often precede bursts. Paroxysmal episodes, sudden violent releases of pressure, can drive sky-high lava jets, loft-tall ash plumes, and blast glowing clasts across wide arcs. Those clasts, called lapilli volcanic bombs, can be as small as gravel or as large as a football, and they travel fast. On busy volcanoes worldwide, people have been injured by projectiles and ash clouds that outran expectations. A grim lesson from New Zealand's Wakari/White Island is that a volcano in routine activity can still switch gears without much warning. Etna is more active than most, so that lesson applies doubly here. Part of the management challenge is Etna's shape-shifting tempo. A cycle can start with tame spattering, leap into fountains, toss short-lived pyroclastic surges, then fall back to a simmer. The newly mapped fracture could mark a deviation from that familiar arc, hinting that structural stress is accumulating in a way that increases the odds of a lateral opening. Italy's National Institute of Geophysics and Volcanology reports ongoing strombolian bursts at the summit with intermittent ash visible from surrounding towns. Analysts watch more than camera images. They track the precise height of advancing lava fronts, monitor the rise and fall of harmonic tremor, and listen for infrasound signatures that reveal explosions even when weather hides the vents. Together, those metrics show magma still moving underground and feeding the surface. Because the system is unsettled, caution is wise. No one can say with confidence how the next day or two will unfold, and that uncertainty is itself a warning sign. Persistent tremor, active deformation, a fresh fissure, and multiple lava sources argue for restraint on the mountain and vigilance in the communities below. A new vent can open with little notice. An existing vent can choke and then clear with more force. Wind can swing an ash plume over a road that was clear an hour earlier. Sicilians have lived with that reality for generations. Ash on the windshield at breakfast and a faint glow on the horizon after sunset are part of the local rhythm. When instruments show rising risk, authorities close trails and restrict access. The latest fracture, together with pressure signals, argues for a stretch of heightened respect. Being prepared, knowing routes, keeping masks, having a communication plan is not alarmist. It is responsible. Round-the-clock monitoring continues. Networks of seismometers listen for swarms, too small for people to feel. GPS receivers and tilt meters register millimeter-scale motions of the ground. Thermal cameras chart the heat of flows and vents. Gas sensors measure sulfur dioxide and other emissions that rise when new magma nears the surface. Drones supply overhead views that ground teams cannot get safely. Together, these tools give a near real-time portrait of Etna's mood and help officials adjust closures and guidance. The broader scientific community follows closely because each Etna cycle teaches lessons that travel. Comparing data from Sicily with other regions sharpens models of magma ascent flank stability, and the thresholds that tip a photogenic eruption into a hazardous one. In that sense, every measurement taken on Etna contributes to the global understanding of how our planet moves heat and material from its depths to the surface. For visitors and locals, the advice remains simple. Enjoy the spectacle from safe lookouts and respect guidance from the park and civil protection. Keep clear of summit zones. While the alert is elevated, the mountain's beauty is real, and so is its unpredictability. Respecting both is how you witness the show, without becoming part of the response. If you're passionate about geology and want more updates as this sequence evolves, stay tuned. We'll keep translating measurements and field notes into plain language. Share your thoughts below. Do you think this fissure signals a larger shift, or will Etna settle back into its familiar cadence? Your perspective helps guide what we explain next, and your caution helps keep everyone safe on the slopes. Quick glossary. Strombolian means rhythmic bursts from gas bubbles at the vent, spectacular but typically limited in range. A paroxysm is a short, powerful peak that can hurl lava high and spread ash widely. Pyroclastic flows are fast, ground-hugging clouds of hot gas, ash, and rock. Rare on Etna, but dangerous enough to drive higher alerts. Lapilli are small cinders. Volcanic bombs are larger blobs that harden in flight. Terms like these explain why rules can change quickly. Last point, volcano science is probabilistic, not prophetic. Analysts merge many weak signals, small gas shifts, subtle tremor, centimeters of tilt, into a picture of rising or falling risk, then revise it as new data arrive. Patience with restrictions and respect for the mountain make safer outcomes possible. Stay informed, stay flexible, and give Etna space. Beneath the roaring winds and icy tempests of the Southern Ocean lies one of the most treacherous waterways on Earth, the Drake Passage. Stretching roughly 404 miles, 650 kilometers, between Cape Horn at the southern tip of South America and the northern edge of the Antarctic Peninsula. This vast corridor of ocean serves as the only natural link between the Atlantic and Pacific. It is a place sailors both fear and revere, infamous for monstrous waves, unpredictable currents, and storms that can rise from calm seas in minutes. Named after the English privateer Sir Francis Drake, who crossed these waters in the 16th century, the passage represents both the edge of human endurance and a natural laboratory of immense geological energy. For centuries, explorers have spoken of its wrath, but what lurks beneath this remote expanse is even more formidable, a dynamic, restless sea floor where the forces shaping the planet collide in silence. On October 10, 2025, this hidden tension erupted in violent fashion. At precisely 8:29 p.m. Coordinated Universal Time, the ocean floor of the Drake Passage convulsed with the force of a 7.6 magnitude earthquake, according to the United States Geological Survey, USGS. The quake struck at a shallow depth of about 6.5 miles, 10.5 kilometers, below the surface, shallow enough to transmit its energy efficiently across the water. Its epicenter was pinpointed at 60.3 degrees south latitude and 61.9 degrees west longitude, roughly 436 miles, 702 kilometers, south-southeast of Tolhuin, Argentina, and 438 miles, 705 kilometers, southeast of Ushuaia, the southernmost city on Earth. Initial seismic readings varied, slightly depending on the monitoring station. The European Mediterranean Seismological Center registered a 7.7, while early data from other international agencies estimated up to 7.8 before revisions refined the analysis. Variations like these are routine in large-scale quakes, as sensors scattered across the planet take time to process and synchronize the complex web of seismic waves. Still, every report agreed on one fact. This was a major tectonic event, one capable of unleashing widespread effects across the southern hemisphere. The relief, if any, came from geography. The quake occurred far from densely populated regions, deep in one of the most isolated corners of the planet. Yet proximity to land was close enough to spark serious alarm. Puerto Williams, Chile, a small but vital settlement on the northern coast of Navarino Island, sits roughly 135 miles, 218 kilometers, from the epicenter, making it the nearest human community to the quake's origin. Further north, the regional hub of Punta Arenas, home to more than 117,000 residents, lies about 590 miles, 949 kilometers away. While infrastructure damage in these cities was not immediately evident, scientists feared a secondary danger that often follows such underwater quakes: tsunamis. Just 19 minutes after the quake struck, the Pacific Tsunami Warning Center, PTWC, issued an urgent advisory for the Chilean coast. Their bulletin warned that hazardous tsunami waves were possible within a 1,000-kilometer radius of the epicenter. Forecast models suggested that the first waves could strike Puerto Williams by 6:36 a.m. local time on October 10th, followed by Punta Arenas several hours later, around 2:49 p.m. The rapid issuance of these warnings underscored the speed and precision of modern monitoring systems, vital tools in preventing tragedies across coastal communities. The Hydrographic and Oceanographic Service of the Chilean Navy, SHOA, quickly echoed the alert, urging vigilance across the entire southern coastline. Within minutes, Chile's National Service for Disaster Prevention and Response, SENAPRED, activated emergency evacuation protocols for all communities within the Magallanes region, the country's southernmost territory. Residents were told to immediately move away from beaches and low-lying areas to elevated ground. Sirens wailed through coastal towns as emergency personnel fanned out to guide families to safety. Radio broadcasts and mobile alerts carried the same clear message. The ocean was unpredictable, and every second counted. President Gabriel Boric, a native of Punta Arenas himself, wasted no time in responding. He suspended his schedule and returned to La Moneda Palace in Santiago to oversee the national response. Through social media, Boric urged calm but firm action, reminding citizens that every resource of the Chilean state was mobilized to confront the threat. Follow evacuation instructions, he wrote. Do not underestimate the sea. His message was amplified across television, radio, and digital networks as Chile's civil defense infrastructure shifted into full emergency mode. On the streets of Punta Arenas, local news cameras captured scenes of urgency mixed with composure. Families carried backpacks filled with essentials, blankets, food, water, documents, as they climbed toward higher ground. Vehicles streamed inland, headlights cutting through the dawn mist as people sought safety. Schools and public buildings on elevated terrain became temporary shelters. Despite the anxiety, the calm coordination reflected a population deeply familiar with living in one of the world's most seismically active nations. Chile has learned, often painfully, that readiness can mean survival. Authorities extended the warning even further south, to Chile's Antarctic research bases. Facilities such as Base Pratt and the O'Higgins Research Station, situated on the Antarctic Peninsula, were ordered to move personnel and scientific equipment to secure locations. Though hundreds of miles away, the unpredictable nature of tsunami propagation meant even these frozen outposts were not beyond potential impact. Scientists stationed there paused their experiments to monitor ocean sensors in real time, a stark reminder that even the most isolated places on Earth are linked by the restless pulse of tectonic forces. Across the border, Argentina also moved swiftly. In Tierra del Fuego, provincial authorities issued precautionary advisories, closing ports and suspending all navigation in the Beagle Channel. The Civil Protection Secretariat halted all aquatic activities and coordinated with the Chilean Navy for joint observation of sea level changes. These actions underscored a vital truth. When nature strikes, cooperation transcends politics. Both nations share not only a border, but also exposure to the same volatile geological systems that have shaped South America's southern frontier for millions of years. The Drake Passage lies at the meeting point of immense tectonic and oceanic forces, where the Scotia Plate, Antarctic Plate, and South American Plate jostle for dominance beneath some of the roughest seas on Earth. It forms part of the Pacific Ring of Fire, a 25,000-mile horseshoe of instability encircling the Pacific Basin. This zone is home to 90% of the planet's earthquakes, and about 3/4 of all active volcanoes. For Chile, earthquakes are not rare occurrences, but an inevitable fact of life, born from the slow, inexorable subduction of the Nazca Plate beneath the South American continent. This process unfolds along the vast Atacama Trench, an underwater scar plunging more than 26,000 feet, 8,000 meters, deep. Every year, the oceanic Nazca Plate creeps eastward at about 2.8 inches, 7 centimeters, forcing its edge beneath the continental crust. The friction builds colossal energy along the fault line, and when that energy releases, the Earth shakes with catastrophic power. The 7.6 event in the Drake Passage is a vivid demonstration of this ongoing planetary engine, one that never truly sleeps. In the hours following the quake, ocean buoys positioned throughout the Southern Ocean detected subtle sea level changes consistent with mild tsunami generation, though no catastrophic surges were confirmed. Chilean naval units deployed reconnaissance aircraft to monitor wave movement, while scientific vessels equipped with sonar systems began assessing the seafloor for signs of rupture or uplift. Though damage to populated areas appeared minimal, the event served as another warning of how fragile the balance between Earth's tectonic plates remains. Geologists are now studying whether this quake may be linked to broader seismic stress transfers along the Antarctic-South American boundary. Some early models suggest the tremor could slightly increase pressure along adjacent fault systems, closer to the Chilean mainland, though the risk remains speculative. Still, each event provides valuable data that helps refine understanding of this volatile region. For the global scientific community, the Drake Passage quake represents both danger and opportunity, a natural experiment in one of the least studied corners of the world. The information gathered from it may improve future tsunami prediction models and help strengthen monitoring networks across the Southern Hemisphere. Natural disasters remind us that even in the age of satellites and supercomputers, the Earth remains unpredictable. What happened beneath the Drake Passage on that October night is not just an isolated tremor. It is a reminder of the forces that shape continents, carve mountains, and command the seas. Humanity can measure and prepare, but it cannot control. If you found this report compelling and want to stay informed about the latest in geology, volcanology, and seismic events, make sure to subscribe and enable notifications so you never miss an update. Share your experiences in the comments below. Whether you've lived through an earthquake, a tsunami warning, or any natural event that changed your perspective, together awareness and knowledge can turn fear into preparation, and preparation into resilience. It's starting to feel like mountains everywhere are loosening at the seams. If you've been tracking the recent run of rockfalls and slope failures, you're not alone. Share your take below on what this means for mountain belts and their valleys worldwide. Let's focus on one case study, Hawk Vogel, rising to roughly 8,500 feet, 2,592 meters. It stands apart in the eastern Algae Alps on the Bavaria-Tyrrell line, a solitary summit that dominates lower neighbors. Long before official records caught up in 1818, local shepherds were already on its ridges. Surveyors later used the peak as a triangulation point during early mapping efforts, proof of how prominent and reliable a landmark it once seemed. That appearance of permanence hides a touchy geology. Hawk Vogel is built mostly of Maine dolomite, a Triassic-age sedimentary rock. It's tough on the whole, but under the right stress, water, and temperature conditions, it can fracture and fail. History bears that out. On May 27, 1935, a massive failure ripped from the southwest face, sending thousands of cubic yards, thousands of cubic meters of rock downslope. More modest slips followed in 2005, 2007, and 2016. In other words, instability here isn't new. What's changed is the pace and scale of warning signs. The headline issued today is a summit-spanning crack that has been widening and deepening. Earlier measurements described a fissure about 130 feet, 40 meters long, approximately 10 feet, 3 meters wide, and approximately 26 feet, 8 meters deep. By 2024, high-resolution monitoring indicated dimensions on the order of 115 feet, 35 meters, in length, nearly 20 feet, 6 meters across, and roughly 20 feet, 6 meters deep. If a major section lets go, estimates suggest as much as approximately 340,000 cubic yards, approximately 260,000 cubic meters of rock could detach. Enough volume to reshape a valley floor and strip trails, alpine meadows, and infrastructure in its path. Since 2014, geoscientists and engineers, principally from the Technical University of Munich and the GFZ Research Center in Potsdam, have run an advanced warning network known as AlpSense Bench. Think of it as a digital nervous system for the mountain. Laser scanners, geophones, crack meters, GPS, and a continually updated 3D twin-track tiny movements down to hundredths of an inch, tenths of a millimeter. The system's goal isn't fortune-telling, it's pattern recognition. When motion accelerates in ways that typically precede failure, The instruments can flag danger a couple of days in advance. Like a weather forecast, it can detect trends and tipping behavior, but it cannot name the exact hour a block will break. Despite the warnings, curiosity draws people in. Hikers still edge toward the open fracture to see the problem up close. That uneasy mix, spectacle and risk, has turned Hochvogel from an icon of alpine beauty into a live hazard zone and one of the most closely watched mountains in the range. Seasonal conditions amplify the threat. As European summers warm, accelerated snowmelt and heavier rain load the rock mass with water. Rain infiltrates joints and bedding planes, acting like a lubricant, while also adding weight. Over the past 5 years, the crack's width has grown by about a foot, approximately 30 centimeters. A small number on paper, but alarming at this scale. The situation echoes a Swiss case near Blatten, where a slope's movement rate jumped from approximately 0.5 inch per day to approximately 0.5 inch per hour, an escalation that made collapse imminent. That is exactly the kind of acceleration the sensors here are tuned to catch. If a major release occurs, modeling suggests debris could surge into Austria's Hornbach Valley near the Germany border. Population in the direct path is sparse, but there are well-used trails, huts, and grazing areas. The consequences for those sites could be severe, even if towns farther away remain out of reach. To manage that risk, authorities have tightened early warning procedures so that rescue teams, alpine clubs, and local administrations on both sides of the frontier receive immediate alerts. With even 2 days' notice, priority areas could be cleared to prevent casualties. One event may not be the end of it. Specialists expect a stepwise breakdown as possible. Phases of failure spread over months or years. That kind of drawn-out destabilization would keep access limited and require continuous monitoring, with ripple effects for tourism and the local economy tied to mountaineering and hut networks. There's also the human layer. For communities that have lived with the mountain as a backdrop, a place of quiet and challenge, the present uncertainty carries a psychological toll. Trails that once felt routine now demand vigilance. The landscape itself feels provisional. Zooming out, Hochvogel's behavior fits a pattern seen across the Alps. In recent decades, extreme weather has become more frequent. Intense rain, hotter summers, and volatile storms. Lightning is under investigation too. Repeated electrical strikes can micro-damage rock, and when you combine that with prolonged saturation from rain, the structural integrity of fractured dolomite can degrade over time. It's death by 1,000 cuts. No single factor explains it, but together they tip the balance. Monitoring continues around the clock. Millimeters matter here. A slight jump in displacement speed can separate stable enough for now from failure in progress. And the hazard isn't only rockfall. Should a large collapse occur, secondary debris or mud flows could mobilize later, potentially traveling into the Hinterbach Valley and creating follow-on dangers. That's why planners are already sketching longer-term protections, not just emergency responses. Add it all up, climate trends, the natural fatigue of an old mountain, human exposure, and the slow arithmetic of geology. And Hochvogel has become a working laboratory. It's no longer just a summit to photograph or bag. It's a case study in how fast solid ground can change. The old cliché, solid as a rock, doesn't land the way it used to when the rock is riddled with widening joints and measurable motion. What does feel solid is the need to respect both the landscape and the science watching over it. If stories like this catch your interest, stick around, subscribe, tap the bell so you don't miss new deep dives, and pass this along to friends who follow natural hazards. And tell us in the comments what you make of the Hochvogel situation, or if you've seen similar slope instabilities on your own travels. Your experiences help widen the discussion. For those who want a little more technical context, consider the mechanics at play. Main dolomite typically features bedding parallel weaknesses and vertical fractures formed over geologic time. Freeze-thaw cycles widen those voids as water expands into ice, and in warmer seasons, infiltrating rain reduces friction along those same plains. Add the occasional seismic vibration, regional earthquakes, or even distant tremors can contribute. And you have a system primed for episodic movement. Each episode need not be catastrophic on its own, but cumulatively, they can reduce the safety margin until a nudge, an intense storm, a temperature swing, or a saturated week pushes the mass beyond its threshold. That is where monitoring earns its reputation. Laser scanners map the face repeatedly, comparing point clouds to detect subtle bulges or overhang growth. Geophones listen for microcracking, tiny acoustic emissions that hint at bonds failing within the rock mass. Crack meters measure aperture changes across the fissure, while GPS monuments track surface displacement. Feed all that into a living 3D model, and you can see which blocks are moving coherently and which are locked, giving responders a target for closures and evacuations that is grounded in data rather than guesswork. The goal is not to eliminate risk, no one can, but to convert uncertainty into informed decisions that save time and lives. The social piece matters too. Messaging must balance clarity and proportion, neither downplay nor sensationalize. Local guides, HUD operators, and municipal leaders succeed when communications are simple, timely, and consistent. Closed today signs need clear detours. Alert levels should be color-coded and explained. Evacuation drills should be practiced in shoulder seasons when routes are less crowded. Small choices like multilingual notices or QR codes linking to live dashboards can save minutes when minutes matter, and visitors can help by treating closures as lines not to be crossed rather than challenges to brag about online. Finally, remember that mountains change on human timescales more often than we think. The Alps are not static museum pieces. They're dynamic landforms shaped by uplift, weathering, ice, water, and gravity. Hawk Vogel is a reminder that beauty and hazard live side by side. Respect the forecasts, heed the ropes, and treat that widening crack not as a spectacle, but as a message from the rock itself. As we wrap up, a quick note on personal responsibility. If you visit this area, plan conservatively. Check current closures, register your route when required. Carry a map and headlamp even on fair weather days, and turn around early if the ground or the forecast feels wrong. The summit will be there tomorrow. Your margin for error may not.